Hello and welcome to the 12th exercise from our signal theory class. In this exercise we will practice discretization. Here I have this circuit, this time continuous system, and I would like to discretize it using different methods. I have already expressed this circuit using the Laplace image of the input voltage, Laplace image of the output voltage, and the impedances of the individual elements. Now to find the transfer function of this circuit, I need to realize that this is basically just a voltage divider. So to express the transfer function, I need to write the impedance of this series combination, that is this impedance, and then I need to divide it by the impedance of this series combination, that is this impedance. When I substitute these specific values of these elements, I will get this expression for the transfer function. This transfer function has these zeros and poles and this frequency characteristic. So it is a low pass with this zero. Now I will discretize this system and I will start with the forward difference. I will use the sampling frequency of 15 Hz. Now for the forward difference, I need to substitute this expression for S in the transfer function. When I express this using the sampling frequency, I will get this, and when I substitute for the sampling frequency, I will get this. So this is my transfer function, and I will make this substitution, which will give me this. In this fraction, I can divide both the numerator and the denominator by 45, and I can also expand this square and this square. That will give me this. Here I just need to collect all the coefficients for the individual powers, which will give me this. And this is the transfer function of my discrete time system. From here I can read the coefficients of the system and I can write the difference equation. When I numerically compute the zeros and poles of this transfer function, I will get this, and when I compute the frequency characteristic of this discrete system, I will get this. Here you can see that the frequency characteristic is distorted. This zero is no longer a zero, and this hump is much bigger than what I had here. And when you take a look at the zeros and poles of the transfer function, you can see why. These zeros do not lie on the unit circle, even though in the continuous time system they lied on the imaginary axis. Therefore, in the frequency characteristic of the continuous time system, I have this zero, but that zero is no longer present in the frequency characteristic of the discrete time system. Also, these poles got closer to the unit circle than they should have, which created this excessive hump. So this is the discretization using the forward difference. With the forward difference, all you need to do is to make this substitution and then crunch the numbers. Also, you should keep your expectations about the shape of the frequency characteristic rather low. Now the backward difference. I have the same continuous time system, except now I will do the discretization using the backward difference. When I want to do the backward difference, I need to substitute this expression for S in the transfer function. When instead of the sampling period I use sampling frequency, I will get this, and when I substitute 15 Hz for the sampling frequency, I will get this. So this is the transfer function of my continuous time system. I will make this substitution and that will give me this. Here I can divide both the numerator and the denominator by 45, and I can expand this square and this square. That will give me this, and here I just need to collect the coefficients for the individual powers of z. That will give me this, and this is the transfer function of my discrete time system. Here I can identify the individual coefficients of the system and write the difference equation. When I numerically compute the zeros and poles of this transfer function, I will get this plot. And when I compute the frequency characteristic of the discretized system, I will get this. Again, you can see that the frequency characteristic is distorted. That is because these zeros do not lie on the unit circle, even though in the continuous time system they lied on the imaginary axis. So even though I had this 0 here, I no longer have it here. So this is the discretization using the backward difference. Again, all you need to do is just this substitution, and then you need to crunch the numbers. Also, you should keep your expectation about preserving the shape of the frequency characteristic rather low. Now the bilinear transform. Again, I have the same continuous time system, except now I will discretize it using the bilinear transform. For the bilinear transform, I need to make this substitution in the transfer function. When instead of the sampling period, I use sampling frequency, I will get this, and when I substitute 15 Hz for the sampling frequency, I will get this. So starting with the transfer function of the continuous time system, I will make this substitution, which will give me this. Here I will divide both the numerator and the denominator by 45, and also I will multiply both the numerator and the denominator by 1 plus z to the minus 1 squared. When I do that, that will give me this. Here I need to expand all these squares, and also I need to expand this multiplication, and when I do that, I just need to collect all the coefficients for the individual powers of z, which will give me this. And this is the transfer function of my discrete time system. Again, here I can identify what are the coefficients of my system, which will allow me to write the difference equation. When I numerically compute the zeros and poles of this transfer function, I will get this distribution, and when I compute the frequency characteristic of my discrete system, I will get this shape. And you can see that now the shape of the frequency characteristic is fairly nicely preserved. Finally, these zeros got to the unit circle, so when I have a 0 here, I will also have a 0 in the frequency characteristic of a discrete system. So this is the discretization using the bilinear transform. Again, all you need to do is just this substitution, except this time you can look forward to the shape of your frequency characteristic being preserved. Now the impulse invariance. I will do the discretization of the same continuous time system as on the previous slides. This is the same transfer function that we had before, but now you can see that the computation is a little bit more bloated, so I did not have room to keep the schematic of that continuous time system here. So, to do the impulse invariance, I first need to find the impulse response. That I will find as the inverse Laplace transform of this transfer function. To find the inverse Laplace transform, I first need to convert this to usable partial fractions. So, the order of the numerator is the same as the order of the denominator, and I have to deal with that first. I will start with extracting this 5/11 in front of the fraction, which will leave me with this numerator. Then in the numerator, I will add 6s plus 45 like this, and I will subtract and add whatever needs to be subtracted and added so that this numerator remains the same. Now I will divide this part of the numerator by the denominator and this part of the numerator by the denominator, which will give me this. Now I will extract this minus 6 in front of the fraction, which will leave me with this numerator. And now I will complete the square in the denominator, and I will write numerator like this. Now I will multiply this 6 and this 1 with this 5/11, and I will separately divide this part of the numerator by the denominator and this part of the numerator by the denominator. That will give me this. And this form is suitable for the inverse Laplace transform. So the inverse Laplace transform of this constant is the Dirac delta function times that constant. The inverse Laplace transform of this partial fraction is cosine of 6t, and because of this plus 3, I need to multiply it by this exponential. The inverse Laplace transform of this partial fraction is sine of 6t, and because of this plus 3, I need to multiply it by this exponential. So this is the impulse response of my continuous time system. Since I'm doing the impulse invariance, in my next step I need to sample this impulse response. I need to sample it like this. And when I substitute n times the sampling period for time, I will get this sampled impulse response. In the lecture, I replaced this Dirac delta function with a discrete Dirac delta pulse, and that is what would happen if you computed this in Matlab using the imp_invar function. But here I will use a slightly different approach. I will use this formula for the Dirac delta function. In continuous time, if you scale the time of the Dirac delta function like this, you can actually write this Dirac delta function in this form. This multiplication will become this division. And formally, I will do that here too. So this multiplication I will turn into this division. And when I substitute for the sampling period the value that corresponds to this sampling frequency, I will get this. In the remainder of the impulse response, I will try to reduce clutter. I will denote this constant and this constant by omega, and I will rewrite this exponential and this exponential like this, which I will write like this. Now I can take the z transform of this discrete impulse response. For that purpose, I will actually use the formulas for the z transform of cosine and sine. In lecture 9, we had these formulas for cosine and sine, and I also showed you what happens when you take the z transform of a signal multiplied by a geometric series. When you combine this formula with these formulas, you will get these formulas for the z transform of cosine and sine multiplied by the geometric series. And these formulas I will use to compute the z transform of these expressions. So when I use these formulas, I will get this. Here I can note that the denominator of this fraction is the same as the denominator of this fraction. So it is very easy to combine these two fractions like this. Here I need to combine this fraction and put them to the common denominator. When I do that, I will get this. And in this long ugliness, I need to collect the coefficients of the individual powers of z, and when I sweat it out, I will get this. And here I can substitute for omega and a what I have denoted by omega and a, which will give me this. And this is the transfer function of the discrete time system. Here I can identify what are the coefficients of the discrete time system, and I can write the difference equation of the discrete time system. Here, as a reminder, I have the distribution of the zeros and poles of the original continuous time system, and this is its frequency characteristic. This distribution of zeros and poles I have computed numerically from the coefficients of this transfer function. And this is the frequency characteristic of the discretized system. You can see that there is a little bit of distortion here because these zeros do not lie on the unit circle. So this is how you do discretization using the impulse invariance. It takes a little bit more computation than the previous discretizations, but for you it is good practice of the Laplace transform and the z transform. Now the matched z transform. I still have the same continuous time system, except this time I'm using the matched z transform. To do the discretization using the matched z transform, I need to find where the transfer function of my continuous time system has zeros and poles. These are the zeros and poles of this transfer function. Then I need to transform these zeros and poles using this formula. When I do that, I will get these zeros and poles. And using these zeros and poles, I will write the transfer function of my discrete system. In this transfer function, I need to expand these brackets, these multiplications, which will give me this. And here I can read the coefficients of my system. Using those coefficients, I can write the difference equation of my discrete time system. When I plot these zeros and poles into the complex plane, I will get this. And when I plot the frequency characteristic of the discrete system, I will get this. And you can see that the matched z-transform is trying to preserve the shape of the frequency characteristic. However, I have to note that for more complex transfer functions, the bilinear transform will preserve the shape of the frequency characteristic more precisely. So when you want to preserve the shape of the frequency characteristic, the bilinear transform is usually the transform of choice. And this is how you do discretization using the matched z-transform. You just need to find where are the zeros and poles of the transfer function of your continuous time system. Then you transform those zeros and poles using this formula, which will give you the zeros and poles of your discrete time system. Using these zeros and poles, you will build the transfer function of your discrete time system. Here I have an example of a zero-order Holt discretization. To spare you some long and ugly computations, I have simplified my continuous time system and now I'm using only this RC circuit. In this RC circuit, I will use these values of the capacitance and resistance, and I want to discretize it using this sampling frequency. To express the transfer function of this circuit, I can use impedances of these two elements and express the transfer function of the circuit using the formula for the voltage divider. So using that formula, I need to divide this resistance by the sum of this impedance and this resistance. I can express the transfer function of my circuit like this. Here I can multiply both the numerator and the denominator by S times C, which will result in this. In this expression, I can substitute these specific values, which will give me this. This I can also write in this form. So this expression is the transfer function of this continuous time system. This transfer function has this zero and this pole, and the system has this frequency characteristic. Now let's do the zero-order Holt discretization. For the zero-order Holt discretization, I need to take the transfer function of my continuous time system, divide it by S, and then compute the inverse Laplace transform of this expression. That will give me the impulse response of this system. Specifically, in this case, I need to compute the inverse Laplace transform of this expression. This S and this S will cancel each other out, so the inverse Laplace transform will be this. And this will be the impulse response of this system. Now I need to sample this impulse response like this, which will give me this. That can be simplified into this, and this can be written in this form. Now, I need to compute the z-transform of this sequence. I need to compute this z-transform, which is this. Now, the last step, I need to take this z-transform and multiply it by 1 minus z to the minus 1. That will give me this expression, and this expression is the transfer function of my discretized system. Here I can read the coefficients of the system, and I can write the difference equation. When I compute what are the zeros and poles of this system, I get this, and the frequency characteristic of my discrete system is this. In the case of this very simple transfer function, there seems to be a good correspondence between the frequency characteristic of the continuous time system and the frequency characteristic of the discrete system, but do not expect that to hold for more complex transfer functions. So this is how you can do the zero-order Holt discretization. The principle is simple, but the computation of the inverse Laplace transform and the z-transform can get a little bit more complicated. Now let's take a look how the discretization can be used to design discrete time IIR filters. At the beginning of the lecture, I told you that to design an IIR discrete filter, I can first design a continuous time filter with a desired frequency characteristic and then discretize this filter and turn it into a discrete time IIR filter that will keep that desired frequency characteristic. Now you know how to do the discretization, and you know that when you want to keep the frequency characteristic, it is best to use the bilinear transform. What you still do not know is how to design a continuous time filter with a desired frequency characteristic. The good news is that the Matlab can do this for you, but even if Matlab can do this for you, at minimum you need to be able to specify the requirements on the frequency characteristic. What do I mean? Ideally, you often want this brick wall frequency characteristic where everything up to some frequency is passed and everything higher than some frequency is suppressed. However, this ideal brick wall frequency characteristic cannot be implemented with a real-world filter. You can only approximate it, and an example of such an approximation I'm showing here with this green line. So in a real-world frequency characteristic, you are going to have some passband where everything is passed with approximately constant gain, and you are going to have a stop band where everything is suppressed as much as possible. In between the passband and the stop band, you are going to have a transition band. In the passband, your frequency characteristic is going to deviate from that ideal gain by some error, or we call it a ripple in the passband, and in the stop band, your frequency characteristic is going to deviate from ideal frequency characteristic, that is from this zero, by some error or ripple in the stop band. Also, there is going to be some top frequency of the passband and some bottom frequency of the stop band. And in between these frequencies, you are going to have the transition band where the filter neither passes nor fully suppresses. This diagram is called the tolerance scheme. This tolerance scheme allows me to specify my requirements on the frequency characteristic. I can say where I want my passband, where I want my stop band, how much ripple I'm willing to accept in the passband, and how much suppression do I need in the stop band. When I specify all these values, I can feed them into some design software, and that design software will fit in this approximation, this approximating function, which corresponds to some transfer function of a continuous time system, and that can be discretized, which will give me my discrete time IIR filter. Now, this tolerance scheme is in linear scale. Oftentimes you will see it in the logarithmic scale. This tolerance scheme is pretty much the same as this tolerance scheme, except here my vertical axis is linear and here I have it in decibels. So what is number 1 here is 0 here, and what is 0 here would be minus infinity here. Some of the approximating functions in the passband deviate only in this negative direction. So you will see a tolerance scheme which in the passband has this error defined only in this negative direction. Now that you know what the tolerance schemes are, before you start designing filters in Matlab, you still need to learn about so-called standard approximations. Standard approximations are functions which are going to be fitted into your tolerance scheme. They correspond to transfer functions which can be either implemented as a continuous time system or they can be discretized to create a discrete time system. Most often you are going to use these standard approximations: the Butterworth approximation, Chebyshev type 1, Chebyshev type 2, and the elliptic approximation. These approximations have different properties which you should be aware of. The Butterworth approximation is smooth both in passband and in the stop band. The Chebyshev type 1 is rippled in the passband, but it is smooth in the stop band, and the Chebyshev type 2 is smooth in the passband, but it is rippled in the stop band. The elliptic approximation is rippled both in the passband and in the stop band. Based on this, you probably like the Butterworth approximation the most, but to create this frequency characteristic, I had to use a system of higher order that I had to use for these Chebyshev approximations, and for these Chebyshev approximations, I had to use a system of higher order than I had to use for this elliptic approximation. Specifically, this frequency characteristic was created by a system with order 14. These frequency characteristics were created by systems with order 6, and this frequency characteristic was created with a system with order 4. When you have higher order system, you will have higher computational complexity, but also your system will be more susceptible to numerical errors. If you round some coefficients of the filter, those systems with higher orders can become very quickly very unstable. Now there is another property that you should be aware of. It is so-called non-linearity of the phase of the frequency characteristic. This is a cryptic way of saying that the filters with these frequency characteristic will delay your signal differently at different frequencies. Remember, when we started to talk about the frequency characteristic, I showed you what is the Fourier transform of a signal which is delayed in time. We computed that it is equal to this, and I told you that this is actually a frequency characteristic of a system that introduces this time delay. And you can see that this time delay is the same for all the frequencies. And with this time delay, the phase of the frequency characteristic is going to be a linear function of omega. This is just a line with slope tau that corresponds to this time delay. If the phase of the frequency characteristic is non-linear, then the system is going to introduce different time delay at different frequencies, which can lead to a distortion of your signal. All of these standard approximations, in fact all the IIR filters have non-linear phase characteristics, so they can distort your signal, but the amount of distortion is going to be different for different standard approximations. The elliptic approximation is the worst, Chebyshev approximations are somewhat better, and the Butterworth approximation is even better. So when you design your filter, you need to pick your standard approximation, and these are the trade-offs that you need to consider in your choice. Let's take a look at how we can design filters in Matlab. In Matlab there are functions for the filter design, but if you do not know these functions, you can use an applet called Filter Designer. In the command window you just type in Filter Designer and hit enter. Matlab will give you this applet, and here you can see the tolerance scheme in which you can specify your requirements for the frequency characteristic. Here you can specify what type of frequency characteristic you want to design. You can design a low pass, which has this tolerance scheme, or you may go for a high pass, which has this tolerance scheme. Now the pass band is at high frequencies and the stop band is at low frequencies. If you decide to design a band pass filter, you will need to specify this tolerance scheme. Now you will have two stop bands that you need to specify. If you go for a band stop filter, you will need to specify this tolerance scheme. Now you need to specify two pass bands. Here you can specify whether you want to design an IIR filter or an FIR filter. FIR filters are never designed by a discretization of a continuous time system. There are different techniques, and one of them is the windowing technique that we talked about in lecture 5. There are different techniques for the design of IIR filters, and some of them can be described as a discretization of a continuous time system. Those will be used when I select one of these standard approximations that we talked about in this lecture. Now I will select the Butterworth approximation, I will design an IIR filter, and it will be a low pass. Now I need to specify these parameters of the tolerance scheme, and I can do that here. I will select that I will put in my frequencies in Hertz. I will set that my sampling frequency will be 4000 Hertz. The top frequency of the passband I will set to 500 Hertz, and the bottom frequency of the stop band I will set to 650 Hertz. The deviations in the passband and in the stop band I will specify in the decibels, and in the passband I will allow 3 decibels of ripple. 3 decibels is quite a lot, but here I am picking it so that you will clearly see those deviations in the passband. In the stop band I will require at least 40 decibels of suppression. Now that I have specified my requirements for the frequency characteristic, I can proceed with the filter design by clicking here. Now my filter is designed, and here I can see its frequency characteristic. With the Butterworth approximation, there is no ripple in the passband and no ripple in the stopband. When I zoom in to the passband, I can see that between 0 and 500 Hz, which is my passband, the frequency characteristic does not deviate from 0 by more than 3 decibels. When I zoom in to the bottom frequency of the stopband, which is 650 Hz, I will see the frequency characteristic gives me at least 40 decibels of suppression, which is what I have required. Also, here I can see that the order of the designed system is 16. So for the Butterworth approximation, the designed system has order of 16. Now let's take a look at what happens when I use different standard approximations. Let's select Chebyshev type 1 and design filter. Now when I zoom into the passband, you can see that it is rippled, and the amplitude of that ripple is 3 decibels, which is as I required. When I zoom into the bottom frequency of the stopband, which is 650 Hz, you can see that filter gives me at least, in fact, more than 40 decibels of suppression. Also note that with Chebyshev type 1 approximation, the order of the filter is now only 7, which is less than I had with the Butterworth approximation. Now let's take a look at what I get for Chebyshev type 2. This is the frequency characteristic for the Chebyshev type 2 approximation, and you can see that it is smooth in the passband. There is no ripple in the passband, but I have ripple in the stopband. And also you can see that that ripple gives me suppression of at least 40 decibels, which is as I have required. The order given by this approximation is still 7, as it was for the Chebyshev type 1. Now let's take a look at what I get for the elliptic approximation. I will get this. I have ripple both in the passband and in the stopband, but the order of the filter is only 4. Here you can pick different characteristics of the filter. This is the phase of the frequency characteristic, this is the impulse response, this is the step response, and this is the distribution of zeros and poles. These are the coefficients of the filter, but they are in slightly different form than you are used to. When Matlab designs a transfer function of, for example, 4th order, it will not give you coefficients of a 4th order filter. Instead, Matlab will break this 4th order transfer function into the product of 2 2nd order transfer functions. And this product of 2 2nd order transfer functions is equivalent to the series combination of these 2 2nd order filters, these 2 2nd order sections. This structure and this structure are theoretically equivalent, but this structure has better numerical properties. It is less susceptible to various rounding errors. Moreover, Matlab will give you the scaling coefficients after each section, which will allow you to scale the signals after each section, and that can help you to improve the dynamic range if the dynamic range of the number representation that you are using is limited. So the Matlab gives you the coefficients of these 2nd order sections. These are the coefficients of the numerator of the first 2nd order section, which means those are these coefficients. These are the coefficients of the denominator of the first 2nd order section, which means those are these coefficients. This is this gain. And here you have the coefficients of this 2nd order section. Now, how can you take these coefficients, put them into Matlab, and perform actual filtering? You can go to File, Export, and here you can choose to save those coefficients into a mat file. And when you click Export, Matlab will create a mat file with 2 variables. In the variable SOS, you will get the A and B coefficients of the individual 2nd order sections, and in the variable G, you will get the vector of gains. I will name my mat file my filter. And now it is saved. Now in the Matlab editor I can load that file my filter, and that will load those two variables SOS and G, where in that variable SOS I will have those A and B coefficients of those second order sections, and here I will have the gains. If I do not want to work with several second order sections, I can convert these into a single filter of higher order, and to get the A and B coefficients of this single filter I can use function SOS to TF, which will give me those A and B coefficients. This acronym stands for second order section to transfer function. And now that I have those B and A coefficients, I can, for example, plot the frequency characteristic of the filter. And here I have my frequency characteristic. Now let's do some actual filtering. I will generate a trivial signal to which I will then apply my filter. So first I will define that my sampling frequency is 4000 Hz, and then I will generate a vector of time which will go from 0 with this sampling period all the way to 50 milliseconds. Then I will generate my signal as a sum of two sine functions. The first sine function will be at the frequency of the top of the passband, which was 500 Hz. And the second sine function will be at the frequency of the bottom of the stop band, which was 650 Hz. And now I can apply my filter. That's it, and I can plot my results. And here I go. And this is my signal X, that is the sum of these two sines, and this is my signal Y, that is my filtered signal. And here you can see that mixture of two sine functions, while here, after the initial startup of the filter, you can see that I'm left with a single sine function. That is because the second sine function has frequency which falls into the stop band of the designed filter. So this is how you can design and implement IIR filters in Matlab.